system theory, Fourier analysis. Seismology has undergone a dramatic change in the past 4 decades, due in significant measure to the increasing use of digital signal processing tools. Chief among these tools is the concept of the Fourier representation of seismic signals. Although no information contained in seismic signals is lost or added when we are passing from the time domain to the Fourier representation, this representation provides us a framework for the determination or the reconstruction of some obscure or hidden aspects of seismic data. Examples: filtering for ground roll and refracted waves, multiple attenuation, up-down separation, and more. Here are our objectives. Our first goal in this lecture is to introduce the Fourier series and Fourier transforms, which are the 2 basic tools of the Fourier representation, generally used in petroleum seismology. To gain more insight into the usefulness of the Fourier representation, we will discuss its application in some of the basic operations routinely encountered in petroleum seismology, such as convolution between signals. Here are some of the key outcomes: the differences between signal and systems, the notion of frequency, the difference between a Fourier series and Fourier transform, the mathematical description of the convolution operation in time and Fourier domains. Let's start by recalling the notions of signals and systems. A signal is defined as any physical quantity that varies with time, space, or any other independent variable. A seismic trace is an example of a one-variable signal. A shock gather is an example of a 2-variable signal. We will sometimes qualify a signal as random when it describes an unwanted behavior, such as random signals, which are also known as stochastic signals. However, when it describes a perfectly predictable behavior, we will qualify it as a deterministic signal, and for short, as a signal. Notice that many perfectly predictable signals are sometimes treated as random signals because we may not be interested in their detailed behavior. Signals can be further classified as continuous or discrete. Continuous signals, say in time, are defined for every value of time, and they take on values in the continuous interval AB, where A can be negative infinity and B can be infinity. Discrete time signals are defined only at certain specific values of time. In addition to representing signals as functions of time, they can be represented as a function of frequency by using the Fourier transform, which is discussed in this lecture. A time signal is periodic if it satisfies the following relation: ut equals u t minus uppercase T. This relation states that if ut is shifted by uppercase T, the resulting signal is identical to ut. Uppercase T is the basic period of the signal. Notice that signals with finite duration are not periodic. Each periodic signal ut has a corresponding transient signal that is identical for one basic period. But outside this interval, the transient signal is 0. So transient signals are not periodic. They constitute good examples of signals with a finite duration. We are interested in transient signals in seismology because we are generally dealing with transient signals in seismics rather than periodic ones. However, it is instructive to study periodic signals and their spectra because they provide a good background for the study of transient signals. In practice, any non-periodic fixed duration signal, for example, a transient signal, can be made periodic by repeating it, usually with a period greater than the fixed duration. A system can be defined as a physical device that performs an operation on a signal. For example, a computer filtering program used to reduce noise interferences on desired signals is a system. In this case, the filtering program performs some operations on seismic signals, that is, seismic data. The program has the effect of reducing the noise interferences from the desired signals. We say that we have processed the data. In a more general sense, software realizations of operations on a signal are examples of systems. Hence, software programs which compose a seismic data processing package constitutes an ensemble of systems. The definition of a system is not limited to software programs or physical devices. Systems are far broader than that. The Earth can be treated as a system because it responds to a source by producing ground motions which are recorded as seismic signals. The source here represents the means by which seismic data are generated. A passive system is one which does not generate an output signal if there is no input signal. The Earth, in the context of earthquake seismology, can be regarded as a non-passive system, as it can generate seismic data in the event of an earthquake without an external input signal. In petroleum seismology, we treat the Earth as a passive seismic system because we assume that it generates a ground motion, that is, an output signal, only if there is an input signal. So here's a question. Is the Earth, in the context of petroleum, passive or non-passive with respect to microseismicity? The output produced by the sum of the number of inputs is the sum of the outputs due to the individual inputs. This property is called superposition. If the input is multiplied by a constant, the output will be multiplied by the same constant. This property is called homogeneity. Time invariance is not important here. In linear systems, in which the elements of the system do not change with time, their response to a given input is independent of the time at which the input is applied. This property is called time invariance. Let's now introduce or revisit the notion of cosine wave. Cosine wave represents one frequency. It is very important to understand the physical and mathematical descriptions of cosine wave in order to master the Fourier series and Fourier transforms. The concept of Fourier representation of a given signal revolves around the notion of frequency. The following question comes directly to mind. What is the frequency of a signal? The answer is easy when the signal is under investigation. It's periodic. We will start by answering this question based on the cosine wave signal, which is one of the simplest real periodic functions, yet very important in the Fourier representation. The cosine wave signal can be mathematically described as follows. ut equals uppercase cosine times 2 pi over uppercase T minus phi. An example of a cosine wave signal is shown here. This signal, which is obviously periodic, is characterized by three parameters: the amplitude, uppercase A, where the maximum value is assumed by u. It is always positive, with the dimension of the phenomena described by the cosine. The period uppercase t in seconds, and the initial phase phi in radians. These three quantities, uppercase A, uppercase t, and phi, are all constants. Frequency of the cosine wave, denoted by f, is the inverse of the period. It indicates the number of complete periods in the time interval between 0 and 1 second. It has the dimension of the inverse of time, 1/seconds, also called Hertz, after the German scientist Hertz. It is customary to use the angular frequency, denoted omega, which is given by omega equals 2 pi f, as it allows us to shorten the mathematical expression of cosine waves to ut equals uppercase A cosine omega t minus phi. The phase phi characterizes the initial position of the cosine wave at t equals 0. As the reference signal, the initial phase phi allows us to determine whether the cosine wave is advanced or delayed with respect to the reference signal. These advances and delays can be expressed in time instead of angles by writing phase phi in the following form. So we can express the delay in radians on seconds. Using a well-known formula of trigonometry, we can alternatively cosine wave in this form, where A equals uppercase A cosine phi, B equals uppercase A sine phi. Cosine waves in this form will be used extensively for the Fourier series analysis. Here is the physics description of cosine wave. It brings out frequency, amplitude, and phase, that is, lowercase f, uppercase A, and phi. Here is the mathematical description of cosine wave. It focuses on the orthogonality cosine and sine function. Uppercase F is the frequency, lowercase a is the scale of cosine, and lowercase b is the scale of sine. There are two functions. Each of these functions contains one frequency. What are these frequencies? Finally, let's turn to Fourier series and Fourier transforms, which are the main topics of this lecture. We will start by Fourier series. Adding cosine waves produces a signal whose character depends upon the frequency, amplitude, and phase of each cosine wave. In this figure, two cosine waves are added. One has a frequency of 10 Hertz, and the other has a frequency of 20 Hertz. The spectrum of the resultant signal is plotted beside the cosine waves. The phase of the 10 Hertz cosine wave has been arbitrarily set at 0. In this figure, 11 individual cosine waves of equal amplitude and 0 phase are added to produce the periodic narrow pulse shown on the top trace. The amplitude spectrum of the pulse consists of a series of lines of equal amplitude at frequencies of 10, 20, all the way up to 100 Hertz. This series of lines is plotted here. The phase spectrum is 0 for each frequency. These results, and those shown in the previous slide, suggest that the process of reconstructing a periodic time signal can be performed by adding individual cosine waves in the form of a series in which each cosine wave has its own frequency, amplitude, and phase. Our next objective is to demonstrate that this observation is correct. Any periodic signal can be decomposed as a sum of cosine waves. This sum is known as the Fourier series. It is well known that if I, j, k is the orthonormal basis of a vector space, any vector x in the space can be uniquely represented as a linear combination of I, j, k. The brackets here denote a scalar product. This description is not limited to the Cartesian vector space. It is also valid for spaces of signals as long as we can define a scalar product in the given space. For a space of square integrable signals in the interval AB, we can define the scalar product as the integral of the product of two functions, say phi t and psi t, assuming that the functions are square integrable signals in the interval A and B. We can also introduce the concept of the orthonormal basis in this space of signals based on the definition of scalar product. Condition that the scalar product is 0 says that every pair of signals of the system is orthogonal, whereas condition that the scalar product of each function is 1 says that each signal is normalized. Now that we have defined the orthonormal basis of the space of signals, any given square integrable signal in the interval AB, say ut, can be uniquely expressed as a linear combination of signals constituting the orthonormal basis. For the derivation of the Fourier series, which is our objective, we are interested in the representation of periodic signals. We consider a space of periodic signals with a period uppercase T. We can define a scalar product for this space. Note that because we are dealing with periodic functions, the integral in the scalar product can go from 0 to uppercase T, or from minus uppercase T over 2 and positive uppercase T over 2, or any other boundaries, as long as the length of the integral is equal to the period uppercase T. The next step is to construct an orthonormal basis of periodic functions with a periodic uppercase T, which can be used to represent any signal of this space. The whole idea of basis representation is to find a set of simpler signals which can be used to reconstruct the complex ones. Cosine and sine signals of period uppercase T are probably the simpler signals of space of periodic signals. Fortunately, this set of cosine and sine signals of period uppercase T constitutes an orthonormal basis in this space. Based on the definition of the scalar product in the previous slide, it is easy to see that the elements of uppercase B verify both the orthogonality and normalization conditions. Therefore, any arbitrary periodic function U with a period uppercase T can be written uniquely as a linear combination of the elements of uppercase B. The sum in blue is called a Fourier series. It is composed of one DC component, A, 0 over 2. a series of cosine terms with frequencies lowercase f1 equals 1 over uppercase T, 2f1, and so on. A series of sine terms with frequencies f1 equals 1 over uppercase T, 2f1, and so on. Notice that the evaluations of the coefficients lowercase a0, lowercase an, and lowercase bn require the evaluation of definite integrals in which the limits are plus and minus uppercase T over 2. But any other interval of length, uppercase T, may be chosen as the interval of integration. Here are the practical steps for computing the Fourier series. For a given signal, ut, compute lowercase an and lowercase bn. Deduce its Fourier series by substituting lowercase an and lowercase bn in the Fourier series. Using a well-known formula of trigonometry, we can alternatively cosine wave in this form. Using again this trigonometric identity, the Fourier series can alternatively be reorganized as a sum of cosine waves in which each cosine wave has a frequency Fn equals n over uppercase T, an amplitude uppercase An, and a phase shift phi n. When lowercase bn is positive, the phase shift is a lag in the range between 0 and pi radians. And when lowercase bn is negative, the phase shift is between 0 and pi radians. The amplitude uppercase An is always positive and independent of the time origin, whereas the phase shift depends upon the location of the time origin. Thus, a periodic function of time can be represented by either of two series, mathematics or physics series. Each series requires that two sets of coefficients be specified by each frequency, either lowercase an and lowercase bn, or uppercase an and phi n. The plot of uppercase an versus the frequency constitutes the amplitude spectrum, and the plot of phi n versus the frequency constitutes the phase spectrum. The computation of these coefficients can be simplified if the time function is odd or even by using the fact that the integral of an odd function between symmetric limits is 0, and the integral of an even function between such limits is equal to twice the value of the integral between lowercase t equals 0 and the upper limit. If ut is a function, the functions ut cosine omega n t is odd, because they are products of even and odd functions. And ut sine omega nt is even, because the product of two odd functions is even. So when ut is an odd function, lowercase a0 equals 0, and lowercase an equals 0. However, lowercase bn is non-zero. Again, the computation of these coefficients can be simplified if the time function is odd or even by using the fact that the integral of an odd function between symmetric limits is 0, and the integral of an even function between such limits is equal to twice the value of the integral between lowercase t equals 0 and the upper limit. If ut is even, the functions ut sine omega nt is odd, because it is a product of even and odd functions. And the function ut cosine omega nt is even because e, the product of two even functions, is an even function. So in the special case where ut is an even function, lowercase bn equals 0. Here are the take-home points regarding the Fourier series of even and odd functions. When ut is even, bn equals 0. When ut is odd, an equals 0. Notice that the Fourier coefficients are determined from even times even and odd times odd only. Also, that the integral of an even function is equal to twice the value of the integral between 0 and the upper limit. Here's the quiz. Calculate the Fourier series of the sawtooth waveform, shown here. We can see that this sawtooth waveform is a periodic signal with a period of 1 second. That is, uppercase T equals 1 second. The calculation of the Fourier series involves the determination of the cosine and sine coefficients an and bn respectively, and the DC value, a0, in the Fourier series. It is first necessary to specify ut within the limits of integration. Within these limits, the sawtooth increases linearly with a slope equal to 2 and passes through the origin. Hence, ut equals 2t, along with uppercase T equals 1. Because the sawtooth waveform is an odd function, we could have concluded that a0 equals 0 and an equals 0 without evaluating the integral. The integral is equal to the area under the product curve 2t cosine 2 pi nt between the above limits. We can see here that the net area under the product curve is 0. Hence, a1 equals 0. Similar graphs of the product curves 2t cosine 2 pi nt would show that the net area under the curves is 0 for any n. Hence, an equals 0, where n equals 0, 1, 2, 3, and so on. This result is expected because the sawtooth is an odd function. Let's now turn to the computation of bn. The plot of the product curve 2t sine 2 pi t is shown here. Notice that the area under the left half of the product curve is identical to the area under the right half. The integral for evaluating bn can be carried over half the range and the result multiplied by 2, because the function being integrated is an even function. This equation can be integrated by parts to the final bn coefficient. As the a0 and an coefficients are equal to 0, the Fourier series representation of the repeating sawtooth is given by a sine series. Here, on the right, are the amplitude and phase spectra for the sawtooth wave as a function of frequency. The sum of the cosine wave of the sawtooth wave is shown on the left. Each successive trace contains one more term than the trace below. As the number of terms increases, the resultant signal approaches the sawtooth waveform more closely. It is interesting to see the effect that changes in the phase spectrum have on the resultant waveform. Here's a quiz. Consider a square waveform as shown here. We can see that this square waveform is an even periodic signal with a period of 2 seconds, that is, uppercase T equals 2. Calculate the Fourier series of the square waveform. Before calculating the AN and BN coefficients, let's look at the graphs of the functions ut cosine pi nt and ut sine pi nt for n equals 1. We can see that the net area for ut sine pi nt is 0. A similar construction for any other values of n, the higher frequencies, which show that the net area of each product function ut sine pi nt is 0. Hence, Bn equals 0 for all values of n. This result can be anticipated because the square wave is an even function. For the product function ut cosine pi t, the net area is equal to twice the area between t equals 0 and t equals positive uppercase T over 2. Let's turn to the calculation of Fourier coefficients. Here is the result of A0 term. For the product function ut cosine pi t, the net area is equal to twice the area between t equals 0 and t equals positive uppercase T over 2. The value of the integral of an is 0 between t equals positive 1 over 2 and t equals 1. Therefore, the upper limit becomes t equals positive 1 over 2. The square wave function is equal to unity. ut equals 1 between the limits t equals 0 and t equals 1 over 2. In this example, uppercase T equals 2, which gives the term uppercase AN equals sine pi n over 2. As the Bn coefficients are 0, the Fourier series that represents the given square wave is obtained as a cosine series. The amplitude and phase spectra are given here. Since uppercase T equals 2, the fundamental frequency and the frequency spacing are equal to 1 over 2 Hertz. Here on your right are the amplitude and phase spectra of this square signal. We also show summation of cosine waves on your left. Each successive trace contains one more cosine term than the trace below. As the number of terms increases, the signal of the sum more closely approaches the square wave. Here's a quiz. Calculate the Fourier series of this waveform, where f0 equals 15 Hertz and f1 equals 5 Hertz. Here's a quiz. Plot the amplitude and phase spectra of this waveform, with t0 equaling 100 milliseconds. Here's another quiz. Plot the amplitude and phase spectra of this waveform, with t0 equaling 100 milliseconds. As we have seen in the two examples in the preceding section, any periodic time signal can be represented in the Fourier domain by an amplitude spectrum and a phase spectrum. Our objective in this section is to establish a mathematical relation known as the Fourier transform, which will allow us to go directly from a given periodic time function to its amplitude and phase spectra, and vice versa. We will also seek to generalize this relation to cases in which the time signal is not periodic. Here is the question of the jour. How can I go directly from the amplitude and phase spectra to the function ut without the cosine and sine series of functions? The answer to this question gives us the fundamental concept of Fourier transform. Let's consider a periodic function ut of a periodic uppercase T and its Fourier series representation. We substitute these well-known formulae of trigonometry, which allow us to replace the cosine and sine with exponential in the Fourier series. By using the fact that the coefficient a minus n equals to an and b minus n equals to minus bn, we obtain a relationship which allows us to predict a periodic function when its amplitude and phase spectra are known. Remember that lowercase ut is the periodic function, and uppercase U n over t represents its amplitude and phase spectrum are known because the coefficients an and bn, which are included in u n over t, allows to determine the amplitude and phase spectra. The relationship which allows us to predict a periodic function from its amplitude and phase spectra is known as the inverse Fourier transform. Similarly, we can also go from amplitude and phase spectrum to recover the periodic function. This relationship is known as the forward Fourier transform, also as the Fourier analysis. In other words, the forward Fourier transform allows us to calculate the amplitude and phase spectrum of a periodic function. Is it possible to extend the definitions of inverse and forward Fourier transforms for non-periodic signals? To answer this question, let's start by discussing the Fourier transform of the transient signal of the periodic square wave signal. Let's consider the three signals shown here on the left. Trace 1 is the periodic square wave example used in a previous section, and trace 2 is the corresponding transient signal. Trace 1 has a period of 2 seconds. Therefore, its fundamental frequency and the spacing between frequency are 0.5 Hertz. Trace 2 is also a periodic square wave, but it has a different period of 20 seconds. Hence, its fundamental frequency and the spacing between frequencies are 0.05 Hertz. In trace 2, we have increased the period by a factor of 10, while decreasing the spacing between frequencies by a factor of 10. Also, the amplitudes at the frequencies that are common in the two cases. The Fourier representation of traces 1 and 2 are shown on your right. As the basic period increases, the spectrum contains more and more frequencies with less and less amplitude. However, at the frequencies common to the two cases, the amplitude per fundamental frequency, or amplitude times period, remains constant, independent of the period. As the period approaches infinity, that is, the transient case, both the amplitude and the fundamental frequency approach zero, but the amplitude per fundamental frequency remains constant. Then the spectrum becomes a continuous function of frequency, rather than a set of coefficients located at the specific frequencies. So the continuous spectrum is the limiting case as the fundamental frequency, 1 over uppercase T, approaches zero. This example shows that the periodicity constraint imposed on the Fourier series representation can be removed by letting the period uppercase T go infinity. some modifications to equations of Fourier transform of period functions, which is the first box here, are required so that these results can be well defined after the limit is taken. It is convenient to remove the 1 over uppercase T factor in front of the integral by multiplying the forward Fourier transform by uppercase T, and then replacing uppercase T, uppercase UN, by uppercase U prime N in both forward and inverse Fourier transforms. Because omega 1 equals 2 pi over uppercase T, as uppercase T increases to infinity, omega 1 becomes infinitesimally small, a condition that is denoted by replacing omega 1 with delta omega. The factor 1 over uppercase T becomes delta omega 2 pi. The new equations of Fourier transform of period functions, with these algebraic manipulations and changes in notation, are given here in the second box. The final step in obtaining the Fourier transform of a non-periodic function is to take the limit of both inverse and forward Fourier transforms of period functions as the period uppercase T goes to infinity. In the limit, the infinite summation in the inverse Fourier transform becomes an integral. Delta omega becomes d omega, and delta omega becomes omega. Uppercase prime N becomes continuous, and the Fourier transform of ut becomes a continuous function of frequency, denoted by uppercase U omega. The result is summarized in the transform pair in blue here, which is known as the classical Fourier integral transform, or simply Fourier transform. Here's the quiz. Compute the Fourier transforms of following symmetrical rectangular pulse of length uppercase T and height uppercase A. The rectangular pulse and its sinc spectrum are shown here. At f equals 0, alpha f equals uppercase A uppercase T, which shows that the DC spectral value is equal to the net area of the time function. Notice that uppercase UF is an even function of frequency, but the phase spectrum is null. Here are fundamental properties of Fourier transform. Basically, the superposition in time domain is preserved in the Fourier domain as well as the homogeneity. The folding of a signal in time is equivalent to taking the complex conjugate of the Fourier transform of the signal in the Fourier domain. Here are additional fundamental properties of Fourier transform. Notice that shifting, differentiating, and integrating in the time domain can be expressed as mathematical products in Fourier domain. The Fourier transform extension to a multivariable signal from the one-dimensional Fourier transform is straightforward. The properties of the two-dimensional Fourier transform are essentially the same as those as the one-dimensional Fourier transform. Here is an example of the two-dimensional forward and inverse Fourier transform for a signal varying in time and space, u, x, t. Kx and omega are the spatial and temporal frequencies associated with x and t respectively. The spatial frequencies are also known as wave number and temporal frequencies simply as frequencies. Although the convolution of signals is a mathematical relation, it is extremely important in seismology because it relates the source signature to seismic data. It basically has three components: the input signal, for example, the source signature in the context of petroleum seismology, the impulse response, for example, the Earth response to the delta function source signature, and the output, for example, seismic data. Our objective here is to introduce the convolution. Before we define the convolution relation, it is useful to first introduce the notion of the impulse response of a linear system. A unit impulse, delta t, as an input to a system, as described here, produces an output signal, ht, which is called the impulse response of the system. If the system is linear, a weighted impulse, uppercase A delta t, produces an output waveform, uppercase A ht, which is identical to ht, except that the magnitude will be modified by factor uppercase A, as shown here. If the system is time invariant, the impulse response waveform will be independent of the time at which the impulse response is applied. Thus, a delayed impulse will produce a delayed impulse response. If the system is linear and time invariant, the sum of the weighted and delayed impulses will produce the sum of the weighted and delayed impulse responses. That is, each impulse will produce its characteristic response independent of all other impulses, and the output will be the algebraic sum of the individual responses. These properties are written symbolically as follows. If the impulse response ht of a system is known, that is, the response of the system to a delta function input, the output of the system is the convolution of the input it by its impulse response. The convolution is given by the following. The physical significance of each term's convolution theorem is as follows. Note that the convolution can be performed in the frequency domain as a product. In other words, we can avoid the integration associated with the convolution operation by working in the Fourier domain. From this illustration, we can see that the convolution operation reduces the frequency bandwidth because it smooths the output signal. Actually, the convolution also extends the duration or the length of the output signal. Note also that the convolution can be performed in the frequency domain as a product of two signals, as we described earlier. Remember, there is a large selection of iMode education lectures, which can further enhance your knowledge of wave propagation, elasticity, electromagnetism, wave field sampling, wave field decomposition, and imaging. Thank you for listening to this iMode education lecture.